Hello friends, welcome to the Formula Engineering classroom. Now in this lecture we will see the capillary effect. So what is the capillary effect is? So capillary effect we can understand like that. If a transparent glass tube is dipped into some fluid, the fluid will either rise or fall from its level in that glass tube. Actually this effect is combined effect due to cohesive forces, adhesive forces and surface tension. So let's understand what is it. So here I am considering a free surface of fluid. This is our free surface of fluid here. This is the level. And let I am considering this fluid is wetting fluid. This fluid is wetting fluid. Means for this the contact angle theta is less than 90 degree. As we know from our previous definition, for the wetting fluids the theta will always be less than 90 degree. So this is fluid, let here is air. So this is the interface of air and fluid, and that if I am saying this is wetting fluid, that I am considering this is water. So this is the interface of air and water. So if there is some free surface, definitely there will be surface tension. Right now, I'm taking a glass tube here, and I am dipping that glass tube into this fluid. Right, so I'm dipping this glass tube that here I'm taking. So this is the glass tube, and I'm dipping this glass tube into this water. Alright, this tube is termed as capillary tube. The dimensions of this tube is very much small, means the diameter of this tube is very much small. This is capillary tube. Capillary tube. Alright, so when I will dip this tube into this fluid, so as we know from the nature of water or wetting fluid, this will try to wet this glass surface. So, and also it will try to spread over this glass surface. So it will look like this one. It will try to spread over here. Sorry, this is look like this one. Similarly here it will look like this one. It will try to spread over this glass tube. Now that if we are considering like that, if we will take from our previous example of definition of wetting fluids, this is look like this one. Alright, and let if I am taking a tangent here, then this angle is angle of contact, that is less than 90 degree for wetting fluids. So this will try to spread over here. Also this fluid will rise in this tube and form a meniscus like that. This is the meniscus. Here is this fluid, that is water in this tube. So as I draw, the level of the water in this tube is here, and the surface of water, free surface of water is here, actual level. So there is a difference in the level, that is the level of the water in the tube is more than the level of water here. So that I'm saying it's H. This height is H, and this is as a tube, so it will form like this one. It is concave surface here, like that. Right, again I am drawing this one. It will look like this one. This is like a concave surface here. So what is the reason of rising this fluid here? So due to the adhesive force, first of all this will try to spread over this one. that's why this meniscus is like that here. This surface you can also consider. Again, if I'm drawing like that, I'm taking tangent of this meniscus like that. So again, this angle is theta, this angle is theta, that is tangent angle, and this tube, this is theta. So also this is theta. So let if I'm drawing this meniscus here, so this will look like this one. This is the meniscus here. So I draw this one. So in this case, if I'm drawing a tangent here and also here, so we can say this one, that is that this is the last tube here. So as this angle is theta, this is also theta here. Now again, in this upper part there is also air and this is water, that's why this is also free surface. So also there is surface tension, and as we know our previous lectures or previous discussion, that is surface tension is a line force. So that surface tension will act over this periphery of this concave surface. The surface tension will act over this periphery of this concave surface. So means that is acting like that, that is acting along this tangent. This is sigma here. They are also acting along this tangent. This is acting along this tangent, that is sigma here. This is acting throughout the periphery. Because surface tension is a line force, so it will act over this periphery. Magnitude is sigma. So as we know, that is this surface tension is a line force, this is acting over this periphery. So the component of this sigma vertically, the vertical component of this sigma, we can write this one. So this is, as I resolving along this theta, this will be sigma cos theta. Alright, similarly if we can take a component this side, this component is sigma sin theta. Alright, so the surface tension component that is acting vertically upward on the circumference is sigma cos theta. So the surface tension force that is acting vertically upward is equals to what? So the surface tension force, surface tension force acting vertically upward is, so component is sigma cos theta, and this is acting over this periphery. So if let d is the diameter of this tube, so we can write into line, the line is pi d. Now as this is in equilibrium state, so we know what is the vertically upward force. Upward force is sigma cos theta into pi d. So to maintain the equilibrium state, there is also a downward force that is acting here. So as there is a rise of fluid in this tube, there is some mass here in this tube, and this mass in the gravitational field, that's why the weight will act here, and that weight will act in downward direction. So that I'm changing the different color here. So this weight is acting downward direction. This weight is of the fluid which is in the tube above this water level. So when I want to calculate weight, I can write that is weight of the fluid is equals to, so the specific weight of fluid into the volume of the fluid. So specific weight of the fluid is W. Alright, volume of this fluid that is in this tube up to the height h in d diameter tube. So we can write this is equals to pi by 4 d square h. Alright, this is the volume, pi by 4 d square h. So this surface tension force is acting in upward direction and this weight is acting in downward direction, and this is in equilibrium state. So for equilibrium state we can equate them. So we can write weight force, that is weight is equal to pi by 4 d square h is equal to this force, that is sigma cos theta into pi d. Alright, so let simplifying this one is out, this is out here. So the height h is equals to, this is 4, this 4 is here, 4 sigma cos theta divided by this w is there and d is also there. So w is there and d is also there. So this is the height of water in this capillary tube. Alright, so now let discuss this formula a little bit more. Now if I am saying for a particular fluid this W is constant, that the specific weight of fluid is constant, it's obvious. Theta is the angle of contact, so for a particular fluid and particular solid surface this angle is almost constant. And sigma is also the surface tension, that is equals to what? That is the force or surface tension due to the interface or free surface. So as the interface is fixed, as in this case the interface is air and water, so this sigma is also fixed. So here we can see this one, that is h. For h sigma is constant, theta is constant, specific weight is constant. So h is variable with diameter, so we can write that is h is proportional to 1 by d. So means if I increases diameter, the height decreases. It's obvious. If I'm increasing the diameter of this tube, the height of the fluid in this tube is going to decrease. So in previous lecture I said that is surface tension force is very much small force and have a significant effect when diameter is, that is dimensions are small. So in this case the dimension d is very much small, that's why you can see this significant rise of water in this tube. If I will increase the diameter of the tube, or actually I am increasing the dimension of the tube, the height of the water in this tube is going to reduce. Alright, so as diameter increases, the height of the fluid is going to decrease. Alright, so this is our first conclusion. In second one, let I'm saying d is constant, means I'm taking the fixed diameter tube every time, but I'm changing the fluid here, and let I'm saying the fluid is non-wetting fluid. So we know for non-wetting fluid, theta is greater than 90 degree but less than 180 degree. So when I put the value of theta that is greater than 90 degree, this whole term will be negative. Alright, we know that is when cos theta term, theta is greater than 90, this whole term will be negative. So means in that case the height is negative. So means we can conclude from this point, that is for wetting fluid the height is positive because theta is less than 90, and that's why we are defining this is capillary rise. And for non-wetting fluid, as this theta is providing this or creating this whole value negative, there is a fall of liquid, that is capillary fall. So the capillary fall will look like this one. So if this is the non-wetting fluid, and if there is some tube here, let this value, so just a minute. So I'm saying there is a tube here. So we know for non-wetting fluid, the fluid will try to contact itself. So it will not try to spread over this one. It will try to contact itself. So it will look like this one. It will contact itself. Alright, and within the tube it will look like this one. So here is fluid. There is also fluid. In the tube here is fluid, but there is no fluid here. There is no fluid here. Alright, so this is the fall of liquid in the capillary tube for non-wetting fluid. That is, for non-wetting fluid, theta is less than 180 and greater than 90 degree. So you can consider here this one. If I am considering this fluid will try to contact itself. So in that case, if I am taking a tangent line here, so this angle, that is theta, that is greater than 90 but less than 180. Similar case here, if I am taking a tangent here, so this angle will be greater than 90 but less than 180 degree. So that's why there is a fall of liquid in this case. So in case of wetting fluid, the weight of the fluid was balancing the surface tension force. But in this case, the surface tension acting in downward direction, like here along the tangent. In the previous case this was along here, in this case this is acting along here, means this surface tension force is trying to decrease the level of the fluid here. So which force is counteracted? So in this case, the buoyant force will counteract it, as there is a displacement of fluid in this capillary tube. So due to this displacement, the buoyant force will act in upward direction and the surface tension force act in downward direction. So if you are resolving this force in vertically downward, so the forces along this one will be sigma cos theta, along this one. Now in this case, surface tension was acting here, so vertical component was this one, that is sigma cos theta, and weight was countering. In this case, this sigma cos theta is try to reduce the level and buoyant force is countering this one. So as we know, that is definition of buoyant force, or we will also discuss in the next or in the further lectures in fluid static what the buoyant force is. But we know the Archimedes principle. Archimedes principle states that there is the buoyant force is the weight of the fluid displacement. So simply in this case, in this tube, the displacement of weight is from here to here. So this is h, that I'm saying this is h here. So this is the displacement of fluid. So what is the displacement of fluid in this case? So weight of displacement of this fluid, so the specific weight of fluid into volume displaced is pi by 4 d square h. So again we are getting same thing, but this force is not acting in downward direction, this is acting in upward direction, because this is buoyant force, and this force, that is sigma cos theta pi d, is acting in downward direction, and they will counter each other. So for the equilibrium state, again we get the same formula. So when you are providing theta is greater than 90 but less than 180, this whole term will be negative, that is h will be negative. So that's why there is a fall of liquid. So our conclusion is that for wetting fluid, there is capillary rise rise, and for non-wetting fluids, there is capillary fall. Alright, so we can say that for wetting fluid there is theta is less than 90 degree like water, and for non-wetting fluid when theta is less than 180 degree but greater than 90 degree, there is mercury, this is water. Alright, so if you are dipping a capillary tube in water, there will be a rise in the capillary tube, and if you are dipping a capillary tube in mercury, there is a fall in the capillary tube. Alright, thank you for the watching. Take care of yourself. See you in the next lecture. In the next lecture we will discuss the fluid static. Goodbye.